salty sea spray keeps lightning strikes away. Although most rain on Earth falls over the oceans, lightning at sea is surprisingly rare, and for decades scientists weren't sure why. A recent study suggests salt spray could be getting in the way of clouds charging up for a lightning strike. Thick clouds that form overhead during storms can become electrified when upward-moving air helps them grow tall enough that the upper parts of the cloud freeze into a mixture of granular, rounded snow pellets called graupel and microscopic ice crystals. As these ice and snow particles bump into one another, they transfer electrical charges. The larger graupel grains tend to become negatively charged, and the smaller ice crystals end up with a positive charge. These charged ice crystals are so light that updrafts of air bring them to the top of the cloud, whereas heavier graupel tend to sink. Over time, this separation generates an electrical field between the cloud's positively charged top and negatively charged bottom. When the charge difference either between the top and bottom of the cloud or between the cloud and the ground grows big enough, lightning strikes. But if large, water-absorbent particles of sea salt, abundant in ocean spray, are present, the tiny droplets that typically condense on microscopic dust and soot to form clouds grow much more rapidly, becoming heavy enough to fall as rain well before the cloud can grow tall enough to charge up. Although this mechanism for dampening lightning at sea has been suggested before, evidence for it had not yet been found in global weather observations. To do that, researchers from China, Israel, and the U.S. gathered global measurements of clouds and lightning strikes, plus the expected distributions of particles such as pollutants, dust, and salt in the atmosphere. They used these records to examine how cloud systems with different combinations of the particles evolved over time, documenting when and if rainfall and lightning occurred. The team found that areas with salt spray see up to 90% less lightning. We were able to separate the effects of the small particles and the large, sea spray, particles, says atmospheric scientist Daniel Rosenfeld of the Hebrew University of Jerusalem, who co-authored the study in Nature Communications. These effects are often ignored when climate scientists try to predict when and where rain will fall, he adds. If you don't take them into account in weather prediction models, and even more so in climate prediction models, you don't get the picture right. You don't get the precipitation right, Rosenfeld says. But the fine particles, called aerosols, are not the only factor acting on clouds' complex interior. Other atmospheric differences over land and the oceans caused by local weather conditions, such as wind and temperature, might also play a role in how often lightning occurs. It is very challenging to single out the aerosol effect from these other weather conditions, based on observational analysis only, says Jiwen Fan, an earth scientist studying interactions among aerosols, clouds, precipitation, and climate at Pacific Northwest National Laboratory. Fan, who was not part of the new study, suggests detailed computer modeling of the processes within thick storm clouds would help further clarify the importance of sea salt spray in determining when and where lightning strikes might occur. Quantum computing is the future, and schools need to catch up. The harnessed power of the subatomic world could soon upend the modern computing industry. Quantum computers are all over the news, and fundamental work on the theory that gave rise to them even won last year's Nobel Prize. But the one place you might not hear about them is inside a physics classroom. And if we have any hope of creating a technology-literate population and developing a workforce for this emerging field, that needs to change. What's a quantum computer? Unlike the computer sitting on your desk, which encodes words or numbers as collections of ones and zeros called bits, quantum computers rely on quantum bits or qubits, which are more, well, dicey, much to Einstein's chagrin. Unlike bits, qubits assign weights to their ones and zeros, more like how you would tailor loaded dice, which means there is a probability associated with measuring either number. They lack a definite value, instead embodying a bit of both states until you measure them. Quantum algorithms run on these qubits, and, theoretically, perform calculations by rolling these loaded dice, causing their probabilities to interfere and increasing their odds of finding the ideal solution. The ultimate hope is that math operations such as factoring gargantuan numbers, which now would take a computer billions of years to perform, would only take a few days on a quantum computer.
This new way of computing could crack hard problems that are out of reach for classical processors, opening new frontiers everywhere from drug discovery to artificial intelligence. But rather than expose students to quantum phenomena, most physics curricula today are designed to start with the physics ABCs, riveting topics such as strings on pulleys and inclined planes, and while students certainly need to know the basics, there's room for Newton and Maxwell alongside Schrödinger's cat. There should to be time spent connecting what they are learning to state-of-the-art technology. That matters because quantum computing is no longer a science experiment. Technology demonstrations from IBM, my employer, Google, and other industry players prove that useful quantum computing is on the horizon. The supply of quantum workers, however, remains quite small. A 2021 McKinsey report predicts major talent shortages, with the number of open jobs outnumbering the number of qualified applicants by about 3 to 1, until at least the end of the decade without fixes. That report also estimates that the quantum talent pool in the US will fall far behind China and Europe. China has announced the most public funding to date of any country, more than double the investments by EU governments, $15.3 billion compared to $7.2 billion, and 8 times more than US government investments. Thankfully, things are starting to change. Universities are exposing students sooner to once-feared quantum mechanics courses. Students are also learning through less traditional means, like YouTube channels or online courses, and seeking out open-source communities to begin their quantum journeys. And it's about time, as demand is skyrocketing for quantum-savvy scientists, software developers, and even business majors to fill a pipeline of scientific talent. We can't keep waiting 6 or more years for every one of those students to receive a PhD, which is the norm in the field right now. Schools are finally responding to this need. Some universities are offering non-PhD programs in quantum computing, for example. In recent years, Wisconsin and the University of California, Los Angeles, have welcomed inaugural classes of quantum information master's degree students into intensive year-long programs. UCLA ended up bringing in a much larger cohort than the university anticipated, demonstrating student demand. The University of Pittsburgh has taken a different approach, launching a new undergraduate major combining physics and traditional computer science, answering the need for a 4-year program that prepares students for either employment or more education. In addition, Ohio recently became the first state to add quantum training to its K-12 science curricula. And finally, professors are starting to incorporate hands-on, application-focused lessons into their quantum curricula. Universities around the world are beginning to teach courses using Qiskit, Cirq, and other open-source quantum programming frameworks that let their students experiment on real quantum computers through the cloud. Some question this initiative. I've heard skeptics ask, is it a good idea to train a new generation of students in a technology that is not fully realized? Or what can really be gained by trying to teach quantum physics to students so young? These are reasonable questions, but consider, quantum is more than just a technology. It's a field of study that undergirds chemistry, biology, engineering, and more. Quantum education is valuable beyond just computing. And if quantum computing does pan out, which I think it will, then we'll be far better off if more people understand it. Quantum technology is the future, and quantum computing education is STEM education, as Charles Tan, the director at the National Quantum Coordination Office, once told me. Not all of these students will end up directly in the quantum industry at the end, and that's all for the better. They might work in a related science or engineering field, such as fiber optics or cybersecurity, that would benefit from their knowledge of quantum, or in business where they can make better decisions based on their understanding of the technology. At my job, I talk about quantum technologies to students daily. And I've learned that above all, they are hungry to learn. Quantum overturns our perception of reality. It draws people in and keeps them there, as the popularity of NASA and the moon landing did for astrophysics. We should lean into what captures students' attention and shape our programs and curricula to meet these desires. For those schools adapting to the emerging quantum era, the core message is simple: don't underestimate your students. Some might hear the word quantum and shudder, fearing it is beyond their comprehension. But I have met high school and middle school students who grasp the concepts with ease. How can we expect young students to pursue this subject when we gatekeep it behind years of pulleys and sliding blocks? Universities should start introducing quantum information much sooner in the curriculum, and K-12 schools should not shy away from introducing some basic quantum concepts at an early age. We should not underestimate students, but rather, we should trust them to tell us what they want to learn, for their benefit and for all of science. If we drag our feet even a little, we all stand to lose the immense benefits quantum could bring to our economy, technology, and future industries.